Good afternoon, everyone. Welcome to Sensor and Process Fingerprinting in Industrial Control Systems with Martin Ochoa. Before we begin, just a few brief notes. Stop at the business hall located in Mandalay Bay, Oceanside and Shoreline Ballrooms, level 2 during the day, and the welcome reception tonight will be there at 5:30 p.m. The Black Hat Arsenal is in the business hall level 2. You can also join us for the Pawnee Awards in Lagoon JKL at 6:30 p.m. tonight. Please silence your cell phone. We appreciate that. And give a warm welcome to our speaker today, Martin Ochoa. Thank you.
Okay, thanks, Angelo, for the intro. Welcome, everyone. It's my pleasure to be here at Black Hat. My name is Martin Ochoa. I'll be talking about sensor and process fingerprinting in industrial control systems. And just so you have an idea on our background, so this is a talk together with Mujib Chaudhry. So I'm leading a research group in industry at Sixtera right now, but not so long ago, I was actually in academia. So I was assistant professor in Singapore, where I was supervising Mujib's PhD thesis on the topic I'm going to speak about today. And my background is on math and systems engineering, while Mujib's is on electronic engineering. And so let's start. So I guess, if you came to this talk today, I don't have to convince you, right, that ICS security is important, critical infrastructure security is important. It's not so hard to, imagine catastrophic scenarios in the domain of, say, nuclear power and so on. So I hope that you all agree with me on that. Perhaps what is not so obvious is that all other domains like water distribution are also very critical. So it's harder to see things exploding here. But there's, for instance, our favorite example in this domain is the Marushi Shire incident in Australia. It's a couple of decades ago already, where this disgruntled employee was hacking onto this water treatment system and was managed to spill raw sewage into rivers, parks, and even a hotel. So it's also very critical to secure those infrastructures. And in fact, we are here in Las Vegas in the middle of the desert. Like, imagine what would happen if we suddenly don't have access to drinkable water. That's kind of very critical, right? So I hope you agree with me on that. On the other hand, we all have probably engineering, research, IT background. We tend to dislike noise, right? Noise is something we want to minimize, we want to get rid of, because it's unwanted, unpleasant. But I hope I can convince you through this talk that noise can actually be useful. We can leverage noise to improve the security of industrial control systems. So what do I mean by noise here? Just to give you a little preview on the following slides. So imagine you have an ultrasonic sensor placed in front of a wall. Neither the wall or the ultrasonic sensor are moving. They're a constant physical distance. However, you will see that the measurement might oscillate a lot. If you sample sensor readings, you will see that the measurement is not always exactly the same. There will be a little bit of variation. And that oscillation is noise, right? So it's not exactly the physical distance, but it's some kind of physical distance plus minus error. So what I want to do today is to first walk you through a testbed that is called SWAT, that is in the Singapore University of Technology and Design, where we did a bunch of experiments. I want to walk you through that testbed, discuss how we can attack this testbed by spoofing sensor data. Then I want to walk you through some known countermeasures, both from the applied world and the research world, to this problem. And I want to introduce how we can leverage noise, how we can exploit noise to raise the bar against attacks here. All right? And then I will have some discussion about more advanced attacks and so on. So what is SWAT? SWAT stands for Secure Water Treatment. And it's a water treatment testbed that was built, generously sponsored by the Singapore government to do cybersecurity research. So this is mainly for cybersecurity research. And it's been around since 2015. It has 6 stages of processing, including UV, chemical treatment, filtration. So, by the way, the specs of the plant, data coming from the plant are pretty open. You can go and download them if you want to check that out. It's meant to be, public research, what we're doing there. And in fact, let me show you a quick video on how the plant looks like. So this is a room in the university. You see this big tank over there. That's about 2,000 liters of water, and we have all the 6 stages of processing. So essentially, raw water is coming into the plant, and then the plant cleans the water, turns it into drinkable water on the other end. Here we have an operator control room, HMI. And it's great to have this plant because if you want to do applied research in this domain, it's very hard to get access to such a system, right? So people are scared that you're going to break something as a researcher, and rightfully so. And this plant is very similar to a real-world plant used from an utilities company. So there was a tender to build this plant that was won by a company that's building real plants, and the specs were defined together with an utilities company. So this is not just a toy plant. I mean, the size maybe is not as big as a real plant, but it's pretty good. So from a network perspective, don't worry about the small print. I just want to highlight that all the so all the physical processes are inside this firewall here. And there are a couple of sub-networks. For instance, the network that connects sensors and actuators to the programmable logic controllers, to the PLCs, so the computers, the nodes that are controlling the process, is called the L0 network. And then the network that connects the nodes among each other, so the PLCs among each other, is called the L1 network, right? And of course, we have a firewall because we don't want to expose this to Shodan or to the internet. We want to protect it, right? So, of course, we want to protect the perimeter. And I thought since this is my first blackhat talk, I wanted to keep it brief for you guys. So this is the main takeaway. And with this, I conclude my talk. Thank you very much. I take the questions now. All right. So why do we need defense in depth in ICS? So there are a couple of reasons. This picture, I swear, is not made up. I took it from a marketing blog that was actually highlighting how cool it is that you can control your plant from Starbucks. But of course, as security professionals, we think this is scary, not fun. And so we have a combination of ICS plus vanilla IT plus the internet that is challenging for security. And we also have motivated attackers, insider threats, insecure updates, supply chain attacks, all the things we have seen in the media the past few years. And on top of that, we have traditionally a lack of authentication and security at these deep network field network levels. So I'm going to explain what I mean exactly by that, but this is a combination we have currently in ICS. So I wanted to give you like a small 101 on how a cyber-physical system works, so an industrial control system. So essentially, you have here an example of a water tank. Okay, some of you are already thinking this is very boring. It's just a water tank going up and down. But this is actually our favorite part of the plant to experiment with for a couple of reasons. So we think it generalizes the kind of the problem to other parts of the plant. And actually, if you manage to damage this pump or to overflow the tank, this is actually causing physical damage. You can break these pumps, are expensive. You can flood the lab. You can produce an availability problem, and so on. And on the other hand, we don't want to do this on the chemical tanks for obvious reasons, because we don't want to, have hazards in the university. So this is our favorite example. So what's going on here? So we have a sensor, and this sensor is sampling, for instance, the level of water And based on the level of water, the PLC is taking decisions on how to control the inflow and outflow of water. So when the tank reaches a certain level that is critically high, then the PLC would say, hey, stop pumping water in. Let's just close the inflow and let's start pumping water out so we can take the tank to a safe level. So this is how things should work. So what about security? So what about attacks? So let us zoom in for a second on how the PLC gets access to the sensor data. So in many plants, like in SWAT, we have a sensor that is actually mainly analog. So there's some kind of cable that is connected to a node, it's called the remote I/O, that is translating this analog signal into digital. And then the digital signal goes through the L0 network to the PLC, and the PLC forwards this to other PLCs if they might need this data. Right? So what do I mean by a lack of authentication at those levels? So if we have an attacker that is playing man in the middle in any of these links, traditional classical IT man in the middle, then there's nothing preventing this attacker to actually spoof or forge these values in many ICS currently. And it's not super trivial to do so. You have to understand the low-level protocols, these industrial protocols that are not standard, but I mean, if you want to do it from scratch, take a while, but essentially once you're able to do it, then you can do this. And so I'm going to define an attacker model here that is both physical and cyber, right? So we have here a cyber physical system that is inspired by many works in the literature. So we have seen papers here at blackhat, DEF CON, Hack in the Box, and in the academic domain talking about attacks to sensors, not only in ICS, but also automotive, drones and so on. And essentially, the physical attacker can replace sensors. For instance, he can just bring his own sensor, plug it in, and replace the other one because his sensor is somehow malicious, rigged, and so on. He can, for instance, swap cables from two sensors, two ultrasonic sensors, or two random sensors to sabotage the plan. He can start injecting noise here, or just say false signals to the analog cable to spoof attacks. And I mean, this has been done. This has been shown in blackhat before, how to physically spoof with sensor data. But he can also, on the other hand, be cyber attacker on L0, L1 networks from the SCADA, any kind of man-in-the-middle attack. He can try to observe, learn data, and try to forge it. Okay, so we open the attacker model like this. So what can an attacker do then concretely? So this is the first example of an attack. I'll call it shameless. It's just a term I coined, never mind. It's shameless because we have a tank that had a certain level of water at a certain timestamp, and then the attacker just breaks in and then claims that now water is suddenly much higher than what it actually is. Right? So because the trust model is that the PLC will trust sensor data coming from the L0 network, L1 network, and so on, it will then take the wrong control decision. It will decide, oh, water is very high, let me close the inflow and open the outflow. And because the real value is very close to 0, then you risk actually to empty the tank and then ruin the pump by pumping dry, essentially. So, and I call this shameless because this abrupt jump, if we just observe the previous value and the new value, we say, okay, this is physically impossible. How come the PLC is not realizing this? But the PLC is trusting the sensor value, and the logic is very simple usually. So by doing so, the attacker is creating like a virtual reality for the control logic, right? So if you can spoof many sensor values, this is not the state of the plan, this is another state. And then you force the control logic to make the wrong control decisions. So let me show you, I hope you can all see this video. So at the beginning, the water is at a certain level. And now we're going to open the valve here. And when the valve is open, then water will start racing here. But we are doing a spoofing attack that shows, I hope you can see it, that the level here is staying stable. So the control logic and the operator will see that water is not rising. Well, actually, water is rising considerably. I mean, this is a slow process. This is 4 times the actual speed because it's a big tank. right? But water will raise by about 10 centimeters. And here we're spoofing the value. We close the vault. We're still spoofing the value. So we're running a man-in-the-middle attack in parallel, constantly spoofing the values. And at some point, I will stop the attack, and you will see a sudden jump here from 628 millimeters to 732 millimeters. Because I stopped the attack, now I see the real value, right? I can do this in many ways, from L0, from L1, from SCADA. There are plenty of ways, but essentially, they are all forging sensor data. So what about defenses? So what do we do against that? What do you think? Cryptography, anyone? Yeah? No? So one natural thought, like if you come from the IT world or from security, like traditional security is like, okay, why don't you authenticate these network links so that the attacker cannot simply do this man-in-the-middle attack, right? So there are a couple of issues with this. Essentially, some of which are historical reasons why we don't do that. Well, first of all, the nodes in ICS are usually very computationally constrained devices. They're embedded devices. So it's hard to put expensive crypto on there because the frequency of sampling of packets is very high. So you don't want to create queues and backlogs. So you have to have fast processors. But that's one reason. Historically, it's not so much of an issue right now with modern processors. The industrial protocols do not support these authentication fields or these cryptographic primitives by default. So you have to hack around that. You have to do encapsulation, or you have to add fields and things like that. But I think more interestingly, it doesn't entirely solve the problem. So if you look at this picture again, it's hard to put cryptography on the analog signal, right? Because this is not a device that typically can handle cryptography. You have to come up with a new kind of device. So once you start authenticating packets in the digital realm, you might already have forged values here. That could happen. On the other hand, you could have also attackers, as I said before, insiders, supply chain attacks, insecure updates that might steal these cryptographic keys. This is possible. And then once you get hold on the cryptographic key, you can start signing forged data, essentially. So this is challenging. So in the cyber physical systems community, more from the research perspective, people have proposed, say, hey, actually you're controlling a physical process. So you know the laws of physics of that process. So perhaps you can model that process, right? And build a so-called model-based countermeasure where what you're going to do is to have a model that tells you an estimate or a prediction of the next value based on the value you have observed in the past. And you can compare against that and then decide whether that makes sense or not, right? So for instance, if you recently observed this very low value, your model could tell you, look, I expect that given the current values of the sensor, the current state of the actuators, your water is going to rise by a little bit, right, in the next few milliseconds. So if you now see this, what I call the shameless attack, then you can detect that and raise an alarm because that doesn't make physical sense, right? So this is neat. This is a nice idea to combine these two things. Keep in mind that one challenge for this is that you have to have a model of the process, and this in water is kind of okay. I mean, it's kind of easy because the system is very stable and the process is very stable. But let's say chemical processes, chemical plants that are very unstable is more challenging to have such a model. Now, another challenge is that let's assume that the attacker now wants to outsmart our model-based defense. He hires a master's student. Now, so this fresh college graduate, he's going to try to outsmart our defense. And so they realize that actually they can do something a bit better, which is instead of jumping from this point to this point in one measurement, why don't we just move slowly, 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 so that we are within the threshold of the prediction of this model, and we, in the end, have a cumulative effect. So the attacker here will start attacking here. Water level is actually never changing in the real physical state. But the attacker is going to move slowly, 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 and over time, this will have a cumulative effect. So this kind of attack is called Stealthy in the literature. I didn't make this up. And this can bypass model-based countermeasures. Okay, so that's a challenge. On the other hand, there is another proposal, which is to use physical invariants. So the idea here is you want to correlate measurements from these different sensors and see if there was a violation to some fundamental law of physics that shouldn't change. So for instance, if you had pressure and sensor level, so the level of water, there should be a correlation between the level and the pressure you're measuring on the bottom of the tank. And if you see a violation of that, then you can raise an alarm. And it's hard to come up with an exhaustive list of such invariants, so you might miss some because you have to do this by hand more or less, although there are some attempts to automatize this. But the bottom line is you cannot change the laws of physics. Right? Of course, unless you are Iron Man, then you can bend laws of physics, but otherwise it shouldn't be the case. Right? So what about noise? And here we come to the central point of the talk. So essentially, the question we're asking here is, can we leverage on sensor noise in order to fingerprint sensors and then complement some of these defenses that we have talked about before? But there's a challenge here, and that is a specific research question we had, and that was, can we distinguish between sensor types, sensor noise coming from sensors of the same type and brand? So let me show you what kind of sensors do we have in SWAT and WADI, which is another test bed we have there. So these sensors are different types: ultrasonic, level, flow, pressure, and so on. What is special about these sensors? I mean, they're very accurate. They're also quite expensive. So this is a challenge if you want to do research, because you would like to see if your research generalized to many, many sensors, and then it's challenging. You cannot buy that many of those. So therefore, we have bought a few of cheaper sensors. So I'm holding one of these in my hand right now. So these are cheaper. We can buy a lot of them, and we can combine our tests between the sensors physically on the plant and our sensors that we bought to do experiments. Okay. So how does sensor noise look like for different sensors? So here I'm showing you different types of sensors and their noise. Do you think their noise patterns are different? Yes, no, yes. Well, they're different colors, of course, but yes, also they look noticeably different, I hope. And so this is just to show that essentially they're all measuring the same constant physical quantity. And what you see are oscillations due to their physical imperfections and many other reasons. And it's not so hard to see that if you take different sensor types, their noise patterns are different, right? So as I said before, the real challenge is to say, if you take many sensors of the same type, can you still distinguish them to create a fingerprint? By the way, we're not the first to explore this topic of sensor fingerprinting. This has been explored in other domains like mobile sensors, clocks, microphones, cameras, but we are among the first to do this on ICS. So what do I mean by the challenges between distinguishing sensor noise of two sensors of the same type? So now here you have measurements of two sensors that are two ultrasonic level sensors, and one in red, one in blue. Do you see differences in their noise pattern? Maybe, I mean, it's a bit trickier, right? So there are a couple of things we would like to have for a sensor, for a fingerprint to make sense. So one thing is that the fingerprint should be stable. Like if you take your human fingerprint, you want it to work 1 week from now, 1 year from now. So we can run this twice, like one day and then the week afterwards, and see if the noise patterns are sort of stable. And we can see that they tend to be stable. I mean, like they seem more or less similar, right? So they didn't change too much. So red versus red, blue versus blue, they are more or less okay. But still, it's challenging to tell them apart. So red versus blue, it's a bit challenging. So again, to sum up, so we have water level that is not changing in these two measurements, it's constant. And we have stable behavior between the runs, but it's hard to see visually the difference between the sensor patterns. So we hire our own PhD, we throw a bunch of math magic at the problem, and what we do is we want to compute some features of this noise so that perhaps we can really see a difference between the sensor measurements. So if we now plot a couple of those features in 3D space, this is just for illustration purposes, we have more than 3 features. You can see that now if we take many, many measurements of the red type and many measurements of the blue type, we can now visually see a difference. So they tend to occupy different regions in the 3D space. So these are 2 sensors, two ultrasonic sensors in SWAT. Now what happens if we take 2 flow sensors in SWAT of the same type, same brand? So we see that actually, again, I mean, this thing is not perfect. Sometimes in a while there's an outlier, like here on the top or maybe here in the middle. But you know, you can visually now tell that there's a difference between these measurements. So what happens if you take now 10 sensors of the same type? So now here on the right, you see measurements, many measurements of 10 sensors, 10 ultrasonic sensors. These are the cheap ones because we wanted to buy a lot of them. And we still see that we have a hope at distinguishing their features. So what we want to do here is to use standard machine learning techniques like supervised learning to build some kind of fingerprint checker, some authenticity checker for the sensors. So what do I mean by that? So the question is, can we distinguish the noise coming from a given sensor? Can we build a fingerprint that distinguishes it from other sensors and hopefully from attackers as well? I will explain what I mean by that. So if you take, let's say, sensor 1 and you take many measurements over time, you can split these measurements into chunks of constant size, let's say. And you need chunks because you want to measure these features that are dependent on time. You cannot measure this instantaneously. You need to observe a little bit of noise. And I will paint them, let's say, blue, and for sensor 2, let's say yellow, right? So what I want to happen is I want to build a black box that if I give it a chunk of the blue type, that I can sort of compute this fingerprint, match it against my machine learning trained black box, and then say, yes, this is an authentic blue sensor 1 fingerprint. If to the sensor 1 fingerprint checker, I pass a yellow chunk coming from another sensor, I should tell, no, this is not a valid fingerprint from sensor 1, right? Just like a human fingerprint checker, so like a actual hand fingerprint checker. So this is the behavior we expect. And actually, if an attacker that is unaware of our detection mechanism is forging a signal without any noise, right? So remember the video I showed you before, I had a constant value. So this value could be just constant flat measurement because it's a digital, perhaps cyber attack. Then I will see no noise. And this should be quite obvious. And this should be really fake value, right? I don't want this value, all right? Okay, so if, not sure how much familiar you are with machine learning techniques, there are a couple of standard ways to measure if what you're doing makes sense. And the standard way is to have at least a training set. So you take measurements of various sensors, like many sensors. You label them, you know which sensor measurements come from a given sensor, let's say sensor 1. And then you train with a subset of these measurements, and then you test against another subset that you have never seen before, and you count how many times your classification was correct, right? So you can call this many things, but this is essentially a binary classifier. So there are 2 classes, authentic, sensor 1, and not authentic. And we did that, and we found, we played with different chunk sizes, and we found that if you take chunks of about 2 minutes, this tends to work best. And in our case, 2 minutes means 120 samples, right? So depending on your frequency, sampling frequency, this might change. So again, remember that it's easy to distinguish 2 sensors that are completely from different types. So there we get 100% accuracy. But the tricky thing is to distinguish between sensors of the same type, the same brand. And in those, we reach up to 99% accuracy in authentication tests. So we played with up to 60 sensors of the same type. And this means, just to give you an idea, so there's 1 false classification, either false negative or false positive. So either we misclassified 1 out of every 100. And if there are chunk sizes of 2 minutes, this means 1 every 3 hours, more or less. So we think this is practical. So it's like your fingerprint checker, your biometric scan, it doesn't always work, right? So sometimes, you get misclassifications. We also, we have been doing this for a while. So we have fingerprints that date back 4 years. And so one question you could ask is this fingerprint stable over time? So for instance, if the sensor gets older, will it degrade its fingerprint? And we realized no, that the fingerprints that we have from 4 years ago still valid, still work. And another thing that you might think is temperature affecting, for instance, the behavior of this fingerprint. And we measure temperature in the lab, which has a wide range from 20 to 35 degrees, depending on time of day, how many people are in the room. And we see that this is still stable. So we try to control for many things here. But note that what I'm talking about here so far is noise of a measurement of a constant physical quantity. However, CPS are controlled at dynamic process. So this works under very controlled conditions. But the next question is, will it work more in general, right? So let me just briefly sum up what we have here. So we can detect these shameless attacks, these abrupt changes, by means of model-based countermeasures alone. We can detect these flat injections, noise injections, by means of these fingerprints. And we could think that even in a stealthy attack, if the signal is very, very flat, that should be very suspicious. We can detect malicious hardware. And the next question is, what about an attacker that now hires a PhD student? And so he wants to outsmart our defenses, and he wants to do something weird. He wants to observe the noise, learn the noise distribution, inject coherent noise, do advanced attacks. So note that I said what we had so far worked with static processes, but in practice, like if you would pour water into a glass, you will see that the water level is not rising like very flatly, very monotonically, but it oscillates. So even if you had a perfect sensor, you would see some noise that is inherent to that process. Okay? So I don't know if you remember the video, the water was actually oscillating while filling up. It was not going like this. So essentially, if we plot how a water tank that was at a constant level now raises until a certain high level and then goes out, water flows out again. If we zoom in, we will see that there is some noise there, right, in the signal. And that noise is a combination of the process noise and the sensor noise. So we have both like that. We cannot split them because we have both at the same time. But what we can do is, if we have a good model of the system, we can compute the difference between the observation and the prediction of our model. And now we have something that we call the residual. There is noise that is oscillating around 0, you see? So this is independent of if you're going up this slope here. If you subtract the prediction from the observation, you will stay, if the prediction is good, you will stay around 0, okay? So this is a luxury we have here in water because we know we have very good models of the process, and we can do this. So what happens if an attacker injects flat noise? So let me point out a couple of things here in this picture. So the attacker starts here, right? So we had water was, I don't know, coming up, and then suddenly the attacker injects this flat signal. So we see that for a while, the prediction matches the observation, but still we get a very weird kind of noise. At some point, the control logic opens the valve, the inflow. So the model expects that now water should rise, but it doesn't because the attacker is spoofing the signal. So that's why we see this jump here, and when the valve is closed, then this stops, and when the attack stops, then we have a big jump because we were forging the level, and the level was actually higher. So what happens now if the attacker tries to do even more sophisticated attack? So this before I show you was just a flat injection. We can detect that because it's flat. But I promise you, I wanted to tackle the problem of an attacker that wants to somehow preserve noise. He's aware of what we're doing. He's trying to do something more clever. So this is a bit tricky, but I hope you can follow with me. So essentially, the attack starts here. So we had water coming down. So the slope had a certain degree, a certain angle. And now the attacker wants to do a stealthy attack, starting at this point, that tries to portray to the control logic that actually water is coming down, but slower than it actually is. So the slope is different, yes? So this is why this is an attack, because if the attack stops, then suddenly water will, the measurement will jump to the actual value, which was much lower. So the actual real slope, the real water level was closer to this green one. But here the attacker is not injecting a flat line in the slope, but he's adding values to the measurement he's observing from the real plant. So if you would zoom in, and I will zoom in a moment, you will see that the slope of the attacker has actually noise. He's trying to preserve the original noise by rotating the degree of the measurement. So he hopes that if we have a fingerprint checker, he will bypass that, right? And what will happen here magically is that because we're subtracting the observation with the prediction, the very interesting phenomenon occurs here, that is the prediction, because it knows the model, is expecting water to go faster down. So when we compute this difference, it will shift the noise of the attacker down in this zero axis. So perhaps it's easier, so the attacker, the attack starts here, ends here, and then we see that this noise is weird. So perhaps it's a bit easier to see this while the attack is happening. So here we have water flowing, coming out of the tank. I don't know if you can read, but this level of water is coming down slowly. And we had an original slope that now the attacker is trying to change, right? So now the attacker is spoofing values, changing the slope. But notice that if we zoom in, we see that the prediction also starts to drift apart from the observation, because the prediction knows the model, and the prediction tries to correct the speed at which water is flowing down. So at the same time, we're creating the residual, and we see that the noise of the attacker is also being shifted because of this subtraction of the observation minus the prediction. So this is, again, a luxury we have in water because the models are so good, and the process is so stable that we can detect this kind of attack. So here you see the attacker was injecting actually something with noise. It was not flat, but we managed to detect it by computing the residual. Okay, and again, how do we evaluate this? How do we know this works in practice or not? Same machine learning evaluation trick. We train with data, test on data. This time, chunks are residuals, right? They're not the noise, pure noise, but the residuals. So we found, again, that a chunk of about 2 minutes worked best. And we tested this in up to 18 processes and their sensors on SWAT. And this time we get a little bit of less accuracy. We get 96%, which means 4 out of 100 are misclassified, but we believe this is still practical because it's unlikely that you get 2 misclassified samples in a row sequentially. So this is very unlikely. And regarding attacks, we played around with many attacker models we could come up, and we think we're detecting all of those. But again, if we have a good model of the physical system. Okay. So what about the architecture? So where do you place this black box? So this is really up to you, but essentially it would be ideal that you can sample or mirror the traffic data from L0 and L1 levels to send then the alarms to the SCADA. But of course, then you open a new can of worms, which is you have to protect that box, and the fun continues. But at least you can catch a lot of attackers that are unaware of this technique, or that if you properly protect it, then you have better security than before. So to sum up a little bit, so we have shown, well, a little bit of the hypothesis that that a fingerprint of sensors exists for ICS. I hope you're convinced now that I show you some evidence that this might work. And to do that, we have tried up to 10 sensor types and up to 60 different sensors per each type. And ideally, we should have thousands so that we can better statistically claim our hypothesis. But as I said, they are rather expensive, the industrial ones. We have shown how this fingerprint, together with process fingerprint, can help authenticating sensor readings, and we get an accuracy that we think is practical, right? Again, physical fingerprints are also not perfect. I mean, this is kind of a machine learning based technique is not going to be perfect. On the other hand, this is just the beginning in a sense, because now the attacker can, so what about the attacker now hires an entire research institute? And this apparently has happened, according to some people. So threat actors might have hired research labs at universities to do strong attacks, as possible. So what then, right? They might think of things that we haven't thought of, and very complex attacks. So, for instance, we know that, for instance, this was an attack against chemical processes. We know that in those cases, it's hard to come up with good models. And if we don't have a good model, we cannot compute the residual. So it will be much more challenging to check for fingerprints. And there are many more things, right? So you can think of very powerful attackers that can do replay attacks and that we are unaware of at the cyber level, and so on. So we have, of course, discussed a lot about these things. It's hard to come up with all possible attacks in security, right? But we have some ideas on how you could detect some of more advanced attacks, like, for instance, placing sensors in front of sensors and then doing challenge-based response attacks. Because under very controlled situations, you know the expected reading of the sensor, there's a change in the noise, there's some interesting things going on, but I will leave this for a future talk, hopefully. I'm running out of time. And yeah, so let me just give you 3 takeaways of this talk. So first of all, I'm not sure if everybody was really aware that in ICS critical infrastructures, oftentimes the field networks are not authenticated at these L0 and L1 levels. Sensor noise can be useful to authenticate sensors without using cryptography. I'm not advocating against cryptography, of course, but we can complement cryptography with things that come from the physical and control theory domain. And process plus sensor noise results in a more robust fingerprint, right? So if you consider a dynamic process and its inherent noise, we have something that is more robust than plain noise in controlled circumstances. So with this, I would like to thank you for your attention and for coming to this talk. So we have a bit of time for questions. So if you have questions, can you come up to the mic so that, yeah, sorry. Yes.
Good afternoon. Thank you for the excellent talk. In the OT and ICS space, we often see organizations that want to have a complement between their security posture and operational efficiency. They want to know how it makes them, how can they make it uptime more, how can they produce better, how can they lower costs. Have you done any investigation into predicting degradation of sensors, maintenance cycles, and or identifying service requirements like obstructed pipe by using the same data, so I can provide the organization both, hey, I have a security thing, I can tell you that someone has replaced your sensor, or hey, I can tell you sensor A is actually degrading, or there's an obstruction in this pipe and you need to send a maintenance person to go resolve it.
Yeah, so no, not exactly. We haven't done that. Thanks for the question. Maybe we can discuss also a little bit more offline about things we have done. We have looked a little bit into degradation of service caused by cryptography for curiosity, and we have measured this extensively, but not necessarily in sense that you asked. But we can take it offline. Maybe Mujib has more things to say. Yeah.
Could you tell us about what's the physical element that you're measuring? I'm sorry if I missed that at the beginning.
The physical,
what's generating the noise that you are measuring?
Right. So yeah, it's a good question. So essentially, like if you have a sensor like this is ultrasonic sensor. So how it works is it sends a sound signal that bounces to measure distance, right? So if you have water, you're measuring, for instance, the level of water. So you'll send a sound that bounces back. But because of many reasons, because of the construction of the sensors, physical conditions, not every time that this thing bounces back, you will get this exact same measurement, right? So this is caused by the I don't know, ultrasonic properties of the signal. I'm not an expert on that side, but essentially this is a characteristic of all sensors, not only ultrasonic, even cameras, like they will take like a little bit differently. They don't measure reality perfectly, but they have imperfections. Every time you measure, there's a small error that changes a bit randomly. So yeah, that's my understanding of it.
For the fingerprint authentication, were you doing a sliding window of 2 minutes, or just like every 2 minutes you can verify the fingerprint?
Every 2 minutes, so chunks of 2 minute size. Yeah. Any other questions?
Your lab, you're very controlled. Have you tried temperature variance to see if the fingerprint changes? And also what happens when you fail over to your backup generator to the fingerprint?
Can you repeat, please? I don't get
Variance based on temperature of the sensor. So if I dropped it by 20 degrees Celsius, I'm in an outdoor environment, does your fingerprint go bad? Or
No,
does it
no.
stay steady?
Right. So what we did was we kept track of the temperature to see if that would impact the noise.
Right.
And we found out it didn't, although it changed between 20 and 35 Celsius because of different times of day and the amount of people that were in the room. So,
Okay.
but it didn't, so it was stable.
Stable. Okay. And what about like if you failed over like a backup generator power source?
I see, I got I'm not sure if we controlled for that. I don't think we did, yeah.
Could you please confirm that you're not doing a frequency domain fingerprint to nod to the limited computation capability that's on the devices?
Again, I'm not doing what?
You're not doing FFTs or frequency domain analysis of the fingerprint because of the limited computation that's available in the boxes?
No, I didn't say that. I mean, we can assume that we have a very powerful box to do the whole fingerprint things. What I said was that you cannot build in very easily cryptography inside the boxes, but that's a different thing. But no, we can do expensive computations on the signal, so that's fine. Yeah.
What's the product you're using to do the fingerprinting, to actually build the models that you overlay your actual process variable on?
Your question was the product?
What's the product that you're actually building the models that you overlay the actual process data onto to see the variance?
Right, so we had a model of the system, which is a mathematical model. It's a linear approximation of the differential equation that characterizes that physical process. And on top of that, we compute the features, and then we use support vector machines. So we use standard libraries for machine learning. So it's everything we build ourselves, essentially. I'm not sure if that answers the question, but.
Okay, so it's just something that you've built. It's nothing that can run live, or is this just
it can
theoretical?
Run live. It can run live. So what I showed the video was actually a live construction of the pseudo, and you have a live detector on top of that is raising alarms if necessary.
Okay, so there's no product that's available to purchase? It's just
No, this is academic research so far. Maybe in the future there will be a product, yeah.
Okay, all right, thanks.
Which learning technique did you use for building checker?
Again?
Which learning technique did you use?
Value technique?
You mentioned the machine learning technique.
Yes.
Yeah, which learning?
Machine learning,
The
yeah.
algorithm.
Support vector machines.
Okay, thank you.
Yeah, supervised.
Only support vector machine, or
I think we played with a
you
couple.
tried several things?
Yeah,
and
I think we tried with a couple,
support
but
vector
that worked okay. So yeah, but you could play around with that, but you already get good accuracy. So yeah.
machine. Okay.
Sorry, one more question. How did you physically collect the data? Where are you physically attaching to collect the data, this noise data, the data that you're calculating noise out from?
Yeah. So I believe that, I mean, in our plant, there's a historian that is keeping, so for our experiments, we're doing it like this. So there's a historian that is keeping all the values of the sensor values, and you can record them for a long time. And we are analyzing that. But of course, if you'd like to deploy this, you might want to have ad hoc, like mirroring of the network, because already the historian, if you're under attack, is easy to fool. So, but we are actually taking data from there. Yeah. Okay, I'm done. Thank you very much.